Welcome to Chibuzor Mathphysics. In today's video, we are looking at Thermodynamics 2 course summary, and this is with Chibuzor Mathphysics. And basically, we want to bring out clearly the concept of the first law of thermodynamics. What actually is the first law of thermodynamics? Imagine if you are given an open valve and you are to illustrate within your mind what energy transformations that will occur as air particles move around within the thunderstorm. What would be your best definition or best answer in this question? Thunderstorms are a great way for atmosphere to release energy. Of course, this energy is what we refer to as the source of heat, because when warm moist air meets colder drier air, the warm air rises, the water vapor condenses in the air and forms a cloud. As the water vapor condenses, it releases heat, which is a form of energy. So basically, in the first law of thermodynamics, we are going to be looking at various forms of energy. Energy comes in a variety of forms. We have what we call the internal energy, kinetic energy, potential energy, mechanical energy, heat, chemical, and even electrical energy. So all these forms of energy is what we bring out clearly when we talk about the first law of thermodynamics. Of course, we know that according to the basic concept we learned in our high school, we learned that energy can neither be created nor destroyed. We can only change or transform these energies into one form to another. So stay tuned to Augustine Chibuzor Mathphysics and enjoy what actually is the first law of thermodynamics. So let us take this. Energy conservation is what we refer to in respect to the first law of thermodynamics. So the first law of thermodynamics, it states that energy is conserved for any thermodynamic system, and that to say that energy cannot be created nor destroyed. Energy can only change from one form to another. It cannot be created nor destroyed. So energy is constant. Energy will always be constant. If you take internal energy and you add kinetic energy, you will get another form of energy, which is potential energy. This will give you another form of energy, which is mechanical. We have heat and we have chemical, and this also will be constant. So all these forms of energy, internal energy, kinetic energy, potential energy, mechanical energy, and heat, plus chemical and electrical energy, will be constant in respect to the first law of thermodynamics. Now let us consider the concept of work when we talk about first law of thermodynamics, or generally, what is the concept of work in thermodynamics? In thermodynamics, work performed by a system is the energy transferred by the system to its surrounding. So we say that work is a form of energy, but it is energy in transit. So a system contains no work, and work is a process done by or on a system. We are going to bring out this concept clearly when we deal with calculation that involves work done in first law of thermodynamics. So in general, work is defined for mechanical system as the actions of a force on an object through a distance. And that's why we have said here that work is equals to force times distance, so that it will give us this equation. That W, which is the work done, will be equals to force times delta X, which is the change in that direction of the force. And that's why we say force times distance. Imagine this small illustration here. So force, if you apply force, it means that it has an impact in that system. So there is some distances that we need to multiply the work with, and that's why we say that work is simply equals to F times D, where work, W here, let's pick a pen, W is equals to work, and this usually is calculated in joules. We have F is equals to the force, and this force will be calculated in Newton. We also have V, which is the distance, and the distance will be equals to the displacement. And this displacement, of course, will be in meters. So it is good to pay attention to this as this will help us drive with calculations. So the first law of thermodynamics, we still continue with our concept of work. We already have this. We already talked about work. Having covered the concept of work in terms of the first law of thermodynamics, we see that work is a mechanical form of energy. Of course, we calculate work using force multiplied by distance. But let us recall the definition of pressure. We used to say that pressure as the physical force, it is defined as the physical force exerted on an object. So the force applied is a kind of perpendicular to the surface of object per unit area, and that's why we calculate pressure to be equals to force divided by area, and this will be equals to F divided by changing X squared, so that we can thus define work in respect to pressure to be the work done, that is delta W, will be equals to PdV, and this will be when we record the definition of pressure. So let us see pressure volume diagram, the relationship between pressure volume diagram, another way of depicting thermodynamic processes. I would like us to consider these processes. We have several kind of processes in terms of thermodynamics. We have what we call the isothermal, we have the adiabatic, we have various forms of thermodynamics processes that we are going to be looking at in this video: isobaric, isochoric. We also have isothermal and adiabatic. But first of all, let us go back and look at the PV diagram, that is the pressure volume diagram, the relationship that involved in thermodynamic processes. The pressure volume diagram, abbreviated as a PV diagram, is a graphical representation of change in pressure with respect to volume in a closed system. You have to note, it is in a closed system. PV diagrams are useful for determining the efficiency of a system, or what we call the work done by or to that system. That is why it was very important and prerequisite that we looked at the concept of work before coming to pressure volume diagram. So the classical example I can give is that of a cylinder and a kind of piston with some type of gas enclosed in the chamber. If we recall that the work of a process in a closed system from state 1 to state 2, this work will be represented, if I want to write it mathematically, we will simply have let's pick a clear pen. We will simply have the work done will be equals to the integral from A to B. Let's say that A is 1 up to 2, and this will be up to PdV. Remember here we've got the work done in times of pressure, and that's why when you calculate the work done, the relationship, if you record the work of a process in a closed system from one state, let's say that that state is from 1 to 2, it will be given and calculated using this formula. So the PV diagram graphically will represent work done by or to a system as the area under the PV curve. The area under this curve, in example of a cylinder and piston, like I mentioned, under different circumstances we can represent some idea like common processes in thermodynamic system. So the 4 most common processes would be isothermal, adiabatic, isobaric, like I mentioned, and we're going to see that in a while. Still on pressure volume relationship, this is what I was simply saying. The work done will be calculated by this initial state up to the final state calculated by PDV. So the work done is the area under the initial to final curve, or what we call the gray area. So first law of thermodynamics in general, internal energy will be equal to kinetic energy plus potential energy. Of course, this is of the molecules in the system. If you consider the molecules in this closed system, it depends only on the current system state, that is PVD, pressure, volume and temperature. It does not depend on the past state. It depends only on the current system state, and it does not also depend on how state changes occur. So changes are the result of external forcing on the system in the form of work or heat. So we say that the change in internal energy will be equals to work in environment plus the heat generated in that environment. So du will be given by negative dw plus dq. So du will be equals to negative pdv plus dq, and this will be our formula for calculating the work done using the first law of thermodynamics. Let's consider thermal capacities. If we look at thermal capacities, that is, we are referring to specific heat. Assuming that a small quantity of heat, that is dq, is given to a parcel with constant mass, the parcel responds by experiencing a small temperature increase, that is specific heat. So we are going to calculate that using mc to be equals to dq divided by dt, and this will bring us to the 2 types of specific heat we have. All these types depends on how a material changes as it receives the heat. So we have a constant volume in this case, and we have a constant pressure. Of course, it is the specific heat at constant volume, and we have the specific heat at constant pressure, and we are going to calculate that using the formula indicated above. Still on the specific heat capacities, we have the one for constant volume, and if the volume is constant, it means that the change in volume will be equals to 0. We can rewrite the first law to be given by this. Instead of du to be equals to negative pdv plus dq, we simply have du to be equals to dq, since dv here is equals to 0, and this applies to the second equation as we are going to use it when we dive into calculations. Just before I summarize this, we conclude our lessons today. Let us look at the types of processes. I've mentioned earlier that we have isobaric processes. Isobaric processes, we looked at the transformation at constant pressure, where pressure with this, the transformation of this will be equals to 0. And the isobaric process can be represented as the isobaric expansion and an isobaric compression. So in the next video we are going to dive into explanation on what it is isobaric, adiabatic, isothermal, and other forms of processes in first law of thermodynamics. I remain your friend Augustine Chibuzor Galagas, and this is what we do in first law of thermodynamics. Hope you have enjoyed the video. Do well to subscribe to this channel, and God bless you.